Have you ever really stopped to think about what happens when you double click an icon? I mean, between that click and your program popping up, there is this incredible high speed drama playing out inside your machine. So today, we're going to follow a single instruction on its journey, from your screen right down into the very heart of the computer, to see exactly how it all works. So there you are, you've written some code, you click run, and poof, a window appears. It feels instant, right? But between that simple click and the result, your command travels through this maze of hardware at speeds that are just, honestly, mind-boggling. So let's trace that path. Okay, so the very first step on this whole journey is translation. You see, the code that we write in languages like C++ or Python or Java, well, it's designed for us, for human brains to read and understand. But the computer's brain, the CPU, it speaks a completely different, much more basic language. And that creates our first big hurdle, the translation problem. And wow, this slide right here perfectly illustrates the gap we need to cross. On the left, you've got a line of C++ code. Simple, readable. On the right, that's what the CPU actually sees. It's machine language, just a raw stream of ones and zeros. That is the only language the hardware truly speaks. So how do we get from our language to theirs? Well, we use this amazing piece of software called a compiler. You can think of the compiler as a master translator. Its entire job is to take our human-friendly source code and meticulously convert it, concept by concept, into that binary machine code that the CPU was built to understand. All right, so our instructions are translated. Awesome. But before the CPU can get to work, both those instructions and any data they need to use have to be loaded into the computer's main workspace. And that workspace is called RAM, or Random Access Memory. The best way to think about it is as the computer's active workbench. It's fast, it's ready to go. Anything the computer is currently thinking about is sitting right there in RAM. But here's the catch. It's also volatile. And that's really just a fancy way of saying it's like a whiteboard. The second you turn the power off, everything on it gets wiped completely clean. So how does the CPU find anything on this giant workbench? Well, RAM is organized like a massive, perfectly ordered street of mailboxes. Every single byte of memory, every little slot, has its own unique address, a number that tells the CPU exactly where to look to grab a specific piece of data or the very next instruction. And not everything fits into just one of these mailboxes. Different types of data need different amounts of space. For instance, a single letter, a char, only needs 1 byte. A standard whole number, an int, usually takes up 4 of those mailboxes. And a really precise decimal number, a double, needs a full 8 bytes. This is how a program knows how much space it needs to reserve on that workbench. And now we get to the star of the show. With all our translated instructions loaded up and ready in RAM, it's time for the CPU to do its thing. And it does this with a simple, relentless 3-step dance. The CPU, the Central Processing Unit. I mean, this is the engine of your computer. It's the brain. Every single thing you see happen on your screen is the direct result of this one little component executing huge lists of instructions, one after another, at an incredible speed. And it all comes down to this never-ending process, the machine cycle. First, it fetches the next instruction from RAM's mailbox grid. Then it decodes that instruction to figure out what it's supposed to do. Is it addition? Is it moving data? Finally, it executes that command. Fetch, decode, execute. Over and over and over. That is the fundamental heartbeat of your computer, and it repeats billions of times every single second. So this brings us to a huge conflict in the world of computer design. The CPU is ridiculously, mind-bendingly fast, but it's always needing to get data and instructions from RAM. And, well, compared to the CPU, RAM is actually kind of slow. This mismatch in speed creates something called a memory stall. The CPU is ready to go, ready for the next thing, but the data it needs is still making its way over from RAM. So the CPU literally has to stop and wait. Now, each wait is just a nanosecond, but when they happen millions of times, that's what you feel as a little stutter in a game or a brief freeze in an application. So this becomes the central challenge for computer engineers, right? How do you solve this waiting game? If RAM is too far away for the CPU to get what it needs instantly, how do you keep that super fast engine fed? Well, the solution they came up with is just brilliant. They gave the CPU its own personal super fast notepad called cache memory.
It's this tiny but incredibly fast piece of memory that's built right next to or even inside the CPU itself. The computer makes an educated guess about what data the CPU is going to need next and preloads it into the cache. That way, the CPU has what it needs right there. No waiting on RAM required.
And just look at this chart. It really puts the speed difference into perspective. Look at that massive bar for CPU cache compared to RAM. We are not talking about a small improvement here. It is a monumental leap in speed. This whole memory hierarchy is the secret sauce that keeps our powerful CPUs constantly working instead of constantly waiting. For decades, the path to faster computers seemed pretty simple. Just make the CPU's clock cycle happen more often. Just make it tick faster and faster. But as engineers pushed for more and more speed, they ran headfirst into a fundamental physical limit. For years, we saw CPU clock speeds just climbing higher and higher. 2 gigahertz, then 3, then 3.5. And remember, that's 3.5 billion machine cycles every second. But then, somewhere around the mid-2000s, those numbers just kind of stopped climbing. So why? The reason is something that engineers call the power wall. It's a hard limit based on the laws of physics, mostly heat and power consumption, that just stops us from making that clock tick faster and faster forever. You see, running a CPU faster takes more power, which creates more heat. A lot more heat. We simply got to a point where the chips would get so hot they could actually damage themselves. At the same time, as we made the tiny transistors on the chip even tinier, they started to leak electricity, which just wasted even more power. Simply cranking up the speed wasn't an option anymore. The whole industry needed a new game plan. The thinking became, okay, if you can't make one brain work faster, what if you could make it work wider? And this led to a pretty revolutionary shift. Instead of one super-fast processor, why not use several processors all working together at the same time? And this idea gave us the modern multi-core processor. A core is basically its own independent processing unit, its own brain, built right into the main CPU. So a quad-core chip has 4 of these brains, an octa-core has 8. This is exactly how your computer can seamlessly run your web browser, a music player, and a word processor all at once. Each core can tackle a different job in parallel. So we got around the power wall by building wider instead of just faster. But of course, that solution brings its own set of really complex challenges, especially when it comes to programming and coordinating all those cores. Which leads us to a final question. What do you think the next big bottleneck, the next wall in computing is going to be?